So thank you so much to Takashi for inviting me here to talk at Recon. And I'm happy to talk about the topic of feature interaction selection and its relationship with interpretability, as well as its relationship with generalization and structured learning. And you can hear me okay, right? So of course, this work is not done alone. And so it's done with my home advisor, Dr. Yan Liu, back at University of Southern California. But then some of the work will also be done here in Tokyo, and that's with Dr. Mihito Sugiyama at National Institute of Informatics. So just to give an outline of the entire talk and what we'll be discussing today, we're going to start off with just an introduction to interpretability and kind of the differences between explainability to get everyone on the same page. And then we'll talk about my favorite interpretable model, which is going to be the generalized additive model. And that will lead us into the feature interaction selection problem and why we need to deal with feature interactions. And then we'll start looking at all of these different applications. So the first one will be sparse interaction additive networks, which is just training neural networks under this GAN framework and under this feature interaction framework. And then we'll look at applications with the Shapley values or SHAP explanations, generative modeling with tensor decompositions, and then we'll have a brief wrap up with kind of the future directions for interpretability and feature interactions. Okay, so let's start with just kind of segmenting what the different sub areas of interpretability are, because I think for people outside the field, it's not so clear what these different terms mean, especially when they have such similar meanings. So interpretability tends to mean these days when you have understandability in your model from the bottom up, which is to say that you always have a glass box model that you can understand, and there's something intrinsic about the model that you're building where you can understand it the entire time. So you can imagine something like you have your typical examples like linear regression and decision trees, which are typically thought to be interpretable because you can understand all of the mechanisms, and also it's pretty easy to visualize after you're done training what you've learned. But explainability, on the other hand, is a top-down sort of approach. So we start with this black box, powerful model, and then we're trying to do some post hoc approximation or some post hoc understanding of what that model has learned. And so then typical examples are something like Lime and SHAP, and those are doing something like a locally linear or local decision tree to be able to fit your data. And so because of these two different approaches, they have different limitations. Interpretability coming from the bottom up has this simplicity limitation where you can't get the model to become powerful enough to accurately approximate the data. So there might be a gap with how much you can actually learn from your data. And then explainability has this different gap where the faithfulness is the major limitation. So your explanation is too simple to actually truly explain the model. And so you have your more complex model and you have your simple explanation, but it doesn't actually recover kind of what the model is doing. And so there are these kind of conflicting objectives as well as these two different gaps. So there's the gap between the model and the data from the interpretability side and the gap between the explanation and the model from the explainability side. And then just to look at some or two specific aspects of an explanation, let's talk about the components of the model, which it's explaining, and then the portions of the data that it's explaining. And of course, when I project down to these two different axes, we're missing a lot of the other important information that's important for explanation. So like, is it useful for this specific task? Is it useful for humans? Is it easy to understand? But ignoring that for now, we can talk about how much of the model do we want to explain? Do we just want to explain the parts, the algorithm that describes it? Like this happens, then this happens, then this happens? Or do we want to explain the whole model as some aggregate function, some holistic representation? And we can also talk about in between that, maybe a modular understanding of the model. And then also, how much of the data are we going to explain at one time? We can explain only one particular data instance, or we can explain the entire manifold that we're trying to predict over. And there's also some in between there. So interpretability is going to lie in this bottom left corner, where we have a holistic understanding of the model, and we have an understanding over the global data space. And the explainability I just mentioned is also trying to holistically understand the model, but it's looking not at the global representation necessarily. And one of the main reasons I wanted to include this chart is to talk about a recently emerging area called mechanistic interpretability. And that's focused not on a holistic understanding of the model, but more kind of a mechanistic understanding of the different parts of the model, which then pushes us more towards the modular understanding. And just to round out this chart, we can go further in that direction and just talk about the description of the ML model, which is to say, like, we have a multi-layer perceptron, it's a linear function, then a nonlinear activation, then a linear function, nonlinear activation. And so we understand all these small pieces, but it's as we put the pieces together where we start to get some complexity. And that's why we would like to be in this bottom left corner where we have a holistic and global understanding, not one or the other. And like I mentioned in the first slide, we'll be focusing on this interpretability, explainability regime where we're looking at a holistic understanding of the model. Okay, so now let's introduce the additive model and we can get into why we need feature interactions. So like I said, with interpretable models, they kind of all start from some interpretable insights or some glass box, easy to understand representation. So decision trees, you have this kind of logical path, you follow this step, this step, this step, and gives you a flow chart. Linear models, you tend to think of, oh, you add the influence of this, and you add everything together. And nearest neighbors maybe is you're looking at the closest sample you have in the training data. So there's extensions in the field of interpretability, perhaps with Rashomon Forest, which are looking at sets of sparse decision trees. There's other work in concept models, which has similarities to nearest neighbors, but we're not going to focus on that today. We're going to focus on the additive model, space of interpretability, and how that's generalizing what the linear model can do to scale to much larger data sets. Okay, so what is a generalized additive model? It's quite simple. So in a linear model, you have one coefficient for each of your features. We'll have D input features, and you train a line to fit each of them with a single coefficient. And what an additive model does is all it does is replace those beta coefficients with some arbitrary function. And now we can learn this arbitrary function, f1 of x1, f2 of x2, etc., all the way to fd of xd. And we're still only going to allow one feature at a time to obey this sort of additive formulation. And why is it called a generalized additive model instead of just an additive model? And that's pretty simply just because we can apply it to classification as well. And then we need to do the same tricks as like logistic regression, where we need to add a logistic activation or a softmax activation at the end of the function. But because we can't directly predict the probabilities in an additive way, but we can predict the log likelihoods in that way. So that's a minor caveat. So then how are we going to actually learn these 1D shape functions? Well, we can do the historical methods of doing smoothing splines or piecewise polynomials, or we can do the more recent approaches of random forests or neural networks. Doesn't matter, take your pick. There's a bunch of considerations when we do that. So historically, we're interested in the number of knots in the spline, which lead to more or less complexity. Similarly, we were interested in the regularization parameters, which lead to more or less smoothness in your data. And then also your model type can lead to different extrapolation capabilities, and sometimes that's desired, sometimes that's undesirable. And all of these are considerations when you're picking which model to put in your function. But let's say that we just use neural networks and train as we will. Then are we done? Do we have a sufficiently capable model to fit all of our data? Unfortunately, the answer is no. And that's because of the XOR problem, the classic problem where we can't just fit a linear function. It won't be good enough. Well, it's because the XOR function. So let's just have our two variables, x1 and x2, uniformly distributed on the square. And let's take the continuous version of the XOR function, which is just x1 times x2. Are we able to write this function x1 times x2 as the sum of a one-dimensional function on the first variable plus a sum plus the one-dimensional function on the second variable? And unfortunately, the answer is no. We're not able to do this. And so even if we have as many nonlinearities as we want in one dimension, it won't be enough. And we need to include the interaction between the two features. And so this will be the feature interaction that we're going to spend the rest of the time discussing. And I just want to briefly mention that it's not just some theoretical problem, the XOR problem. This is some example data set where you can see the goal is to predict the number of bikes that are rented every hour. You can imagine a more recent example might be those scooters that are everywhere. And you're trying to predict based off the time of the day of the week, the weather, the temperature, all these different features. And there's an interaction between what time of day it is, the hour of the day, these 24 hours, and then whether it's a workday or a weekend. And so then in order to predict this, you can see spikes in the darker color at 8 a.m. and 5 p.m. or 17 o'clock, where people are traveling to work and from work. Whereas on the weekend, in the lighter color, you can see there's demand that kind of exists throughout the entire afternoon. And so if you don't have both of these pieces of information at the same time, you'll never be able to predict the number of bikes that are going to be rented. And so this is a two-dimensional feature interaction existing in real data. So what is a feature interaction in general? There's an interaction between k different features when we can never write that function as a sum of lower dimensional subsets, functions over the lower dimensional subsets. So here I have the three-dimensional equation written out, which says that the 1, 2, 3 function can be written as a sum of 1, 2 plus 1, 3 plus 2, 3. No matter how complex we make these two-dimensional functions, there's something fundamentally three-dimensional about this function, and that will be called a three-dimensional feature interaction. In k features, the same thing is true. We just need all k features at the exact same time, and we can never write it as a sum of k minus 1 dimensional functions. Okay, so then for a function of d dimensions, let's define this decomposition called the ANOVA decomposition, which pushes as much as it can into the lower dimensional, which is to say we have this function that we're trying to fit f, and we take the one-dimensional functions and we get them as close as we can to the d-dimensional function, right? And then we add to that two-dimensional functions and we try to make it as close as we can with the extra capacity, and then three-dimensional, and then so on. And we know that if we go all the way to d dimensions, then we can fully represent the function because we have the same capacity in the final interaction term as we did in the original function. But now we've kind of pushed as much as we can down to the simpler components. So the 1D is representing as much as it can. The 2D is representing as much as it can. That was not represented by the 1D. And so this ANOVA, or this functional ANOVA decomposition, kind of purifies the interaction so that each component here is measuring only that interaction term. So then let's try to change the notation a little bit to a set-based notation. You can see the order doesn't matter on ij or ijk for the 2D and 3D terms. So we can just consider it as a set, a subset of the features. And we can see we added first all the one-dimensional subsets, then the two-dimensional subsets, then the three-dimensional subsets. And we have a function for each of them. But we can just put all of those together and write it as just the sum over all subsets. And this will be our functional ANOVA decomposition. And we'll also introduce the notation of bracket D, which is just the set of features 1 through D, and then the power set of D, which is just all subsets of the features. So here's the power set representation for just 4 features. We can see there's 16 different subsets we're interested in. And then this functional ANOVA decomposition is providing a decomposition into all these different components. And the really important thing, or one of the main important things, is that Sobel indices, as they're called, can decompose the variance of our original function into all of the different feature interactions. So this sum that we had over all feature interactions then decomposes in the variance space as well. So I'm writing it as the mean squared error, but we can write it as the variance equally well. So the variance of the original function is the sum of all the variances of the smaller functions. And this is in the case where the input features have to be independent. But in this case, we get a very clear-cut way to measure the strength of each feature interaction because all of the different components are split out exactly into what can be seen as a 1D feature interaction, a 2D feature interaction, etc. Okay, so now that we can measure the strength of these different feature interactions, we'd like to introduce the problem of feature interaction selection, where we're going to pick the most important ones of those. And you might be able to imagine for 4 dimensions, we already have 16 feature interactions. For realistic data sets, we're going to have much more. So we need to introduce this problem of feature interaction selection. So first, let's just talk about feature selection, considering just the linear model case, where also for our convenience, we'll just have mean-centered and unit variance input features. So if we fit a model where we pick only a subset S of these features, our error with infinite data can be calculated to just be the sum of every beta term we did not include squared divided by the norm of the beta squared. So that's our R squared value, and we'd like it to be small. So we would like these beta J squareds to be small, which means we need to pick the large beta to include and not include the small beta. Okay, but why would we not just pick all the beta and learn all the beta? Well, that's because of the high dimensional setting. So in high dimensional statistics, there's the scenario where your number of features is much larger than your number of samples. And so this always takes us into the regime of sparsity, where we can't recover all the beta. So we don't want to recover the small beta, and we just try to look for the largest beta. And it's historically known that least squares will overfit. We need to use lasso or best subset corresponding to L1 or L0 regularization. And then we'll kind of induce some sparsity on our terms. So if you haven't seen this before, these are kind of the coefficient strengths, and just the fact that they're on the x-axis is them staying close to 0. And this regularization will allow us to fit better, or rather generalize better, to unseen data because of how little samples we have. Okay, so then if we do that, our error can instead be written this way, where we remember that our beta I hat cannot be exactly equal to beta I. And so then accordingly, we want to include those where our beta hat can be close to beta I and not include those where it will be far away. And this is with respect to, on quote unquote, on average, with respect to our data sampling. So for each data set of our small size n that we get, on average, can we get close enough to be smaller than the noise that we will typically have? So when beta J squared is really small, it's hard to get a better estimate than this small value. But when it's large enough, then typically even with our small number of samples, we can get closer to 0. All right, so feature interaction selection, we're going to do the exact same thing, except now we're going to deal with the functional ANOVA equation instead of the linear equation. And so instead of picking our individual features I, we're going to now pick our feature interactions, which we remember correspond to subsets. And then once we pick a set of subsets, that will correspond to some collection I, which is a subset of the power set. Okay, so instead of all possible subsets, now we're going to consider a collection. And so this sum over S, we have to consider, again, in infinite data, we have to consider those which we did not fit into the model. And following the same Sobel variance decomposition, we can see we just are left with all the error for the terms that we did not fit. So these are all the feature interaction terms which we did not include in our model, and we have the variance of that function, again, R squared normalized by the original function. Okay, so then just to draw these parallels, for feature selection, we need to pick important features, which are I in the set of D, and that leads to a selection S star, which is a subset of D. And then in the feature interaction case, we're now picking S, which are in the power set of D, and our final selection is a subset of that power set. I star. So that's our collection I star. And then there's all this notation about the power set. So we have I in the power set, or I in the original set D, S in the power set, I in the power set of the power set, which is why I is a subset of the original power set and S is a subset of the original set. So it can be a little confusing, all this notation. But if we imagine feature selection, we have our 4 features, we're picking from those. Interaction selection, we have our 2 to the 4, and we're picking from those. So this picture hopefully should still remain clear. If we have our 4 different input dimensions, feature selection picks which of those we're going to include, and feature interaction selection is now picking how we can combine those together with our additive model. Okay, and because this is such an important point, I think I will pause here for just a second to make sure everyone's digested. And then I think we have a Zoom audience as well. If anyone in there would like to ask questions, that would be a great time. Is that in the chat? Okay. Is the variance decomposition always valid? The variance decomposition is dependent on the fact that we have independent input features. So the output variable has full dependence on the input features. In fact, it has like a d-dimensional dependence on the input features. But the variance decomposition is only in the case where we have independent input features. And the situation gets a lot more complex when you have correlated input features. Okay. So if everyone feels comfortable with this general setup of the interaction selection problem versus the typical feature selection problem, then I think we're good to move on. And so then the next thing I'll quickly say is just that the reason I mentioned that feature interaction selection is a generalization of feature selection is because after we have our selected features, we can then just correspond that to a set of interactions by taking all possible subsets. So here we can see we had all subsets which don't include 4 and which do include 1, 2, 3 corresponding here. So this is a more general problem, but it also has more complexity, more combinatorial complexity because of that. And again, why do we need to select? Well, because of the high dimensional statistics regime, like we only have finite data, except now we're even more likely to not have enough data because now to fit all the feature interactions, we need 2 to the d, like data on the scale of 2 to the d, but rather we typically expect that 2 to the d is much larger than n. So even for small tabular data sets, 10 to 20 features, 2 to the 10 or 2 to the 20 starts to be much more than the data we actually have available. And so this is a sort of medium dimensional regime where we still need to obey these laws of only having finite amount of data. However, this regime is different from the high dimensional regime where we typically expect the features themselves have larger magnitude than n. And so again, we'll have these parallels with the feature selection case where we can choose to model some of these I features, and we want that our estimates are close enough to beta I. In the same way, for feature interaction selection, we want that our FS hat estimates are close to FS for those that we choose to include in the model. And so we have the same expectation with respect to the data set of hoping that our model can be closer than the original function. So why can't we just apply some typical high dimensional statistics approaches like a shrinkage estimator or some L1 regularization? And that's because even specifying all these terms now is exponentially many. So if I have 10 features, 2 to the 10 features is starting to already push it. 2 to the 20 features is maybe too many to actually specify even for a simple linear model. And so we can't actually fit anything with a shrinkage estimator anymore. And so we'll need this new key ingredient, and that's going to be heredity. And this will help us search over the power set. So there's a strong version which says that an interaction exists between I and j if I is itself important and j is itself important, and then a weaker version which says the interaction between I and j can exist if I exists or j exists. And this we'll use to then create an algorithm which starts at the bottom of these feature interaction sets and then slowly builds up higher and higher. So this algorithm I've written here, we just get the next set according to our heredity measurement, heredity strength, and then we do a measurement on the those for what could be important. So let's say we look at first all the one-dimensional pairs or one-dimensional sets, and then we have some measurement which says which of those are important and which of those we're going to throw away. So red is going to be those that we're including. And then if we were actually doing a GAN model, we would train it right now. But let's say we're just going through the algorithm. So now we're going to look at our next set of interactions, and we're going to look at the two-dimensional pairs. So 1, 2, 1, 3, and 2, 3. That's because both of their components are already included in the model. And that will let us not check these other interactions, which allows us to more easily explore the space and not deal with the exponential explosion. So let's say we add them, then we can search over triples, add. In the weak heredity case, we can follow the same procedure. Let's say we also get 1, 2, 3. But now we're going to search over the larger space because of our weaker condition. Let's say we get this. We can then, again, because of the weaker condition, look at all the triples. And let's say for this, then we don't explore the fourth dimension. So this is the way that we're going to approach doing this, which will allow us to scale to tabular data sets of like 10 to 50 different features. And so now let's kind of shift into application. So the first thing we're going to do is train a neural network with this procedure. And that's going to be called sparse interaction additive networks. So this sparse interaction additive network, all it's doing is obeying the sparse referencing the feature interaction selection aspect, and then the interaction being, of course, the feature interactions. So on the far right, we have this generalized additive model, which is obeying this particular power set. So 1, 2, 1 and 2, 3, 4, 3 and 4. And so that's the GAM structure, the feature interaction structure that it's obeying. And then in the work, we just figure out how to train a neural network in this fashion by creating the architecture in a specific way. And then this interaction selection algorithm, I've already kind of detailed some of what we do, but the key thing I left out is how are we actually going to measure this heuristic of whether it's important or not. So I told you there's the Sobel variance decomposition, which is a measurement of the feature interaction strength. But in practice, we need some approximation of that. Even in the case where it's correlated, then it won't perfectly correspond to the Sobel variance decomposition anymore. So what do? So what we do is first we just train a vanilla neural network, and then we apply some explainability technique on top of that to get the insights from the model. So we're actually training a deep neural network. We're seeing, hey, which interactions do you think are important? What looks like it's important to you? We distill that information into some symbolic information in terms of feature interactions. And then we're going to apply that to construct the architecture, right? And so we have this original trained model. We have the distilled information based on this FIS algorithm, and then we construct it into a new architecture. And that new architecture we then train. And we see that, yeah. Yeah. Yeah.
So we better if we search firstly search for maybe the combination of two elements, and then find that it's more important, and then go back to the first layer. Maybe is that?
Yes. So I wrote it in this way. One for presentation clarity, but two, so we'll do it that way here because we'll only be training 1, 2, 3 models, let's say. But yes, there are cases where it would be, if you're trying to look at kind of the Pareto optimal curve of like smallness to best performance, there are cases where you would want to go pick a 2D term and then come back later, pick a 1D term. Exactly, yeah. So in the later application, we'll see exactly where that can happen. But for this one, what we do is we're just training at stage 1, at stage 2, at stage 3, and at stage 5. So 5-order interaction. And what we see here is that actually the neural network trained with this distilled information will outperform the original neural network that we had trained. So after distilling the symbolic knowledge, it can do even better because of this regularization procedure that we're adding. So basically on a bunch of real world tabular data sets, we see that we get consistent improvement over the deep neural network in a vast majority of cases, and then competitive performance across all. In fact, our model is doing the best case on average in terms of rank, so it's the most robust across data sets. But there's these 2 data sets where the deep learning still outperforms the cyan model. And those cases are where we have significantly more data than the other data sets. So the Higgs boson data set has 11 million samples, and then the Song-Year data set has 500,000 samples. And here we can see that deep learning is outperforming every other approach. So while cyan was competitive with all these other machine learning approaches, for the other data sets here, like deep learning is just blowing everything out of the water, even your typical tabular approaches like random forest, SVM, XGB. And so deep learning is really powerful when we have all this data to learn from, and it can automatically find its own biases. Another important thing to note is that when we look at increasing the complexity of the feature interactions, we see that the performance continues to drop in this column and continues to improve in this column. So as we continue to add this complexity, we have enough data to continue to fit. So actually, one could imagine that if we go beyond order 5, for these 2 specific data sets, actually we might see some further drops in error. So that's one of the key aspects to note from the results. And then also, because we're training additive models, there's a lot of these interpretable insights that we have into what we've learned. So I kind of touched on this earlier, the bike sharing data set, where we have the important 8 o'clock a.m., 5 o'clock p.m. Spikes in activity, as well as the weekend having a general spike. And then there's this other trend that is going to be the temperature. So people like going outside when it's hot, but when it gets too hot, they kind of don't go outside any more than they otherwise would. And so, yeah, this kind of does get back to your point of there could be an important 2D and an important 1D, and we don't want to add all the other 1Ds before having to look at this 2D one. And so this particular example can explain 80% of the variance of this real world data set. And so even for those of you in the audience who have no experience with this data set, I would say that this summary statistic is actually giving you a really good insight into what the actual data says in the first place. Just with these 2 trends, just with these 2 shape functions, can communicate a lot of that information. So if you imagine it was originally in Boston, if you imagine you're at the city hall for Boston talking about this program that you instilled, maybe this would be an important plot to show. Okay, and then here is another data set, and this is just to emphasize the difference between interpretability and explainability. This is the California housing price data set. And so this is the state of California. And then we have the desirable coastal regions. This is around San Francisco. This is around Los Angeles. And we have the highest prices around those areas. And on the interior, in this mountainous and desertous region, we have much lower predicted prices according to the model. But what we have in the explainability case is that there's kind of a paucity of data. There's a sparsity of data within this desert and mountain region. And so if we're going to try to predict what the model would predict in these regions, we wouldn't have enough really data to understand. We'd have to extrapolate beyond the data that it's been trained on, and then we'd be unclear on how it will choose to generalize. Whereas with the additive model, we can exactly see what it has decided to extrapolate with. Okay, and then also in these safety critical settings, there's the considerations of correlation versus causation. So this is some medical example where we're trying to predict the risk of mortality versus some score of how conscious or alert a person is. So 3 of 15 is the worst score, 15 of 15 is the best. So you imagine as you get better and better scores, you should have lower and lower risk of mortality. However, at a certain point, actually, you can get better and better, but your mortality risk then increases. So what could be happening? There's some other healthcare examples where this is due to the excess care that you're getting. So a nursing staff is not going to see that you have a poor score in your consciousness and not be alarmed by that, right? And so you'll receive this additional care because of this situation. And that can lead to these kind of unintuitive things in the data where we're learning the correlations from the data, and this is what the correlations say, but that's not what we need to consider from a causative perspective. So there's also the example of asthma reducing the death risk of pneumonia, which is a lung disease, and it's known to have high impact for asthmatic patients. And so again, it's the additional care, as well as those older than 100 years of age, then also having a reduced risk of mortality, which can be due to this overcare phenomenon, but also due to the kind of survivorship bias of people that have made it that far in their livelihoods. So there's all these considerations we need to make, and without interpretability, it might be hard to have these insights into the data. Okay, so now we can talk about Shapley explanations, which is quite a popular approach recently, and then its connection with additive models. So for those unfamiliar, the feature attribution methods are just taking your original function and then trying to say, okay, how much of each feature was important for this particular prediction. And then for one data sample, you can say, okay, this is the feature I was looking at, this is the feature I was not looking at. SHAP has gained a lot of popularity because it has these specific axioms based on the Shapley value, which is a historical game theory-based approach. And because it obeys these axioms, it's a unique solution after you take these axioms as fact. So if you haven't seen these before, I'd say 3 and 4 are not that interesting. It's just to say you don't have any a priori knowledge on which feature should or shouldn't be important. And then 4 is just saying if it's not important, then you'll give it 0 value. But then these two, efficiency and linearity, I'll try to convince you basically mean that it's additive. And that will have a nice correspondence with being an additive model. But just to look at what they are or what they kind of seem like, they're sort of just a locally additive explanation. So we can see here, if we were to plot the linear coefficients of our learned linear model, there's kind of a correspondence with the SHAP values and what's being understood from them. So if we go back to our picture of a linear model versus an additive model, SHAP is just, we plug in our particular data, then we compare it to a baseline, probably 0, and then we take the difference between what would normally be predicted at 0 versus what is currently being predicted. And so the Shapley value essentially just returns you the height of these different functions. And so from the additive model perspective, you can see if you plug in a linear model or if you plug in an additive model, all the Shapley value does is split it back apart into these different components that made it up. One thing I want to emphasize is that it's not a linear approximation, like it has no slope information. So linear can be thought of as like constant slope, and then when you're plotting the coefficient, you're plotting that slope. But that's not what's happening here. You're plotting the value, so the slope times the actual feature value, which then corresponds to the additive model case. So you're only looking at the height. So it only has this local information, which is why Shapley is a local explanation approach. And then what function has this specific equation? Don't worry too much about it, but this is the specific functional form that comes from the Shapley value. It has this other form, which can be thought of as the averaging over all permutations. And in practice, this is typically how it's sampled from data with this permutation sampling. But I'm going to kind of spoil it for you from this additive model perspective and feature interaction perspective. There's a really nice clean equation we can use, which is about the quote unquote synergies from the game theory stuff. But you can just imagine the synergies are what's coming from the feature interactions. So without having both features at the same time, we can't use their synergies, which is using them at the exact same time. And so if we go back to our functional ANOVA decomposition where we pushed everything down as far as it can, then what does the Shapley value do? It takes each of those interactions. So let's say we're the feature I and we're sharing with the feature J, and we're talking about the unique 2D contribution that we had. Well, how are we going to split it between ourselves? Let's just split it in half. So the Shapley value splits that feature interaction in half, gives half of it to the first feature, gives half of it to the second feature. And so there's this term in where we just take all subsets where I is a member and then split it amongst the different absolute value of S different interactions. So we're uniquely sharing between the interaction, and that's when we're using this functional ANOVA decomposition. Okay, so then that just kind of paints us a nice picture of the sort of spectrum in this particular additive model framework, because we can talk about the black box to the SHAP explanations to the GAM interpretations, right? And so if we go back to the same data set, this kind of gives us a clearer picture of, okay, what if we just plot the original function that we're learning? It can be hard to understand which are the important trends for it. If we look at the Shapley value, we can get a much cleaner approximation, a much cleaner understanding, but there is still some like kind of overlay because all the feature interactions are kind of be plotting on top of each other, whereas maybe the true interaction structure is more complex. And so you're getting these overlapping interferences where you can't necessarily see what's happening. And then when you talk about the GAM case, then you're completely decomposing it. And so you can actually see exactly where these influences are coming from in terms of your input features. So that's the connection with the Shapley value of this work. And then now we'll talk about one more application with generative models, and that'll be connected to tensor mode interactions and tensor decompositions. Okay, so what's another important class of additive models? If you've taken a statistics course, you've probably at least heard about the exponential family. And then if you haven't heard it before, then I'll say basically it covers any distribution that you've seen, or not any, but a large majority of the distributions you've seen before. So Gaussian, exponential, or Poisson, et cetera, et cetera. And if you don't believe me that it is a linear model or an additive model, then let's take a look at what happens when we take the log probability and then ignore the influence of the renormalization score. Then we see that it's just our theta I parameter multiplied with our TI feature, or in statistics, it's usually called the sufficient statistic. But we can just think about this as features multiplied together with our parameters. Okay. But what we're actually going to do in this work is we're going to focus on the tabular case where we have discrete data. And there we're able to use all of the tools from information theory. So because we have the compact domain, we don't have to worry about our tails and everything, and we can use information theory. So here we're just going to have our d-dimensional data again, and we're going to represent it as like a tensor, or at least think about it as it being represented by a tensor, where each of these categorical features can take I1, I2, I3, etc., different values. And so we can write this as a tensor where we imagine your coordinates describe each data sample has its coordinates corresponding to which I1 event it has, each I2 event it has, each I3 event it has, and that gives it a one-hot tensor just at that location. And if we were to take the probability over all possible features, so again, we're going to apply it to tabular data sets, so that creates a distribution over the possible categories we can have, and that creates a distribution over the entire tensor. And so if we had this tensor in theory, then we can just take the log probability and then train some model to accurately map to the log probability of that tensor. So what we'll do is consider what's called the log linear model. And that's doing the exact same sort of GAM structure. So here my features are very simple for, let's say, I1, it's just a feature for being on this axis, on this axis, on this axis, etc. So there's no actual features, just the one hot. And then we're going to keep the interaction structure, the feature interactions between all the variables. So I'll also just quickly collapse this indicator function so that way it's a little simpler to write. And so this is the log linear model for our discrete distributions. Let's look at a specific case with three-dimensional. We have the normalizing constant, which we have to fit to make it equal to a probability distribution, which sums to 1. And then we have the one-body terms, the two-body terms, and the three-body terms. And just to kind of clarify the notation, we're going to call these mode interactions instead of feature interactions to emphasize that we're dealing with the generative case. And so one body, if we only include those, that's going to correspond to a product of independent distribution. And so then that's kind of the simplest thing we could learn, right? If we look at including all the two body, then we'll have a Boltzmann machine. And so that's also received a lot of historical attention, how to train Boltzmann machines with these data parameters. And then if we go to three body, we'll get a higher order Boltzmann machine and we can continue on. But you can maybe imagine we're going to play the exact same game where we do feature interaction selection to pick the best ones to include. And so there's some work that also does this sort of selection property, and that's called graphical models or sparse graphical models, or also Markov graphical models. So if we look at a Gaussian distribution, I've just written out the formula here, but I've written it with the precision matrix omega instead of the typical sigma matrix. But you can see this is just a log probability of the Gaussian. And what we do with graphical models is we try to learn the omega. Particularly, we try to learn a sparse omega, where the sparsity is corresponding to this Markov property where two features are conditionally independent, or they're independent from one another, conditioned on everything else. And that will correspond to this Gaussian sparsity. And this has also received a lot of historical attention. But what we're going to do is focus on the tabular case where, because Gaussians can only have one body and two body, right? There's no way to represent three-body interactions within a Gaussian because there's no higher order covariance or higher order cumulants in a Gaussian. So we'll focus on this tabular case. And here we're going to see the exact same procedure where feature selection generalizes to feature interaction selection, and graphical model selection corresponds to this mode interaction selection. So again, we'll pick a collection that we're going to include our theta parameters, and then do the exact same game that we played before. And there's some work that exists doing this. So it's called the hierarchical log linear model, hierarchy then corresponding to that heredity condition we talked about earlier, where we're building up from the bottom. But it can also be seen as a sparse higher order Boltzmann machine, right? Because we're including all the higher order terms, but in order to fit that in real data, we need to add some sparsity. So what are some of the limitations of these previous works? Well, everyone has to face this challenge of computing the partition function. So it's quite old by now, like all this Boltzmann machine stuff, but I promise you basically every problem that comes from this is the fact that we can't compute the partition function and the corresponding issues to deal with there. And there's many different approaches, but these previous works are having some issues as well. So like dealing with only binary features, not bigger categorical features. They can't actually train on the log likelihood function or the KL loss objective function because of the inability to compute the partition. And then they're also using L1 regularization, which means you have to tune the lasso parameter at the end of the day. So we're instead going to borrow some of this theory from information geometry and from tensor decomposition to try to tackle these all at the same time. And how we're going to do that is there's I won't go too much into detail, but basically, if we were to pick a collection, then there's a unique space defined in this probability space based on all models we could fit with this. We can talk about the minimization problem of minimizing KL, and that defines a unique projection onto that submanifold. So then if we define like a sequence of interactions we had, which is going to be called a filtration of these collections, then this defines like a sequence of distributions that are being projected onto submanifolds. And this gap between the last projection to the next projection can be some positive value that we're going to call the refined information. And it's always positive and can be seen as this KL term based on the two distributions. But the moral of the story is that our KL error can be exactly decomposed. So in the same way that we had the variance decomposition from earlier, we can decompose all of the important information, all the important error information into each of these different interactions. So this is our ST corresponding to our sequence of feature interaction. And then hopefully that'll be okay. Then we can have each of these corresponding to the error. So let me try to wrap this up. But we'll do the exact same thing. We're going to do a very similar algorithm where we're selecting these interactions, which are important. And here specifically, we will do what we mentioned earlier, where sometimes we want to add the 2-body before we add the 1-body, and then 3-body before we add the 2-body. We're using some heuristic again to do this. But here we can see the classical overfitting, underfitting curve. So in the darker color that goes all the way down, that's going to be our training data. And then in the lighter color that tapers out, that will be our validation data. And according to this equation that I just mentioned, summing the refined information, we should see that this tapers off exactly, and there should be 1 point for early stopping. And so that will be what we do in practice. We'll just early stop as soon as the validation gets worse. And so that's theoretically supported by the previous slides. And this is also on real world data. So in the interest of time, I won't talk too much about the properties of refined information, but basically it's a generalization of mutual information, which generalizes from 2 dimensions to higher order dimensions, so higher order interactions, and also has some ability to deal with the more nuanced structure from local correlations based on the other variables that are part of the model. Here's some synthetic experiments where we show when you match the structure correctly, you can get more accurate estimates with fewer samples of data. And then here's our real world experiments. So we see that our model is able to get better performance than either the 1-body or the 2-body distribution in terms of this generative model scoring. And then we also see that the classification performance is coming out of the box when we train some generative model. So we can compare against logistic regression, for instance, which is performing the best, but we have to train a new regression model each time for each new feature we want to predict. Whereas the generative model is like an energy-based model, and it can automatically predict all of these at the same time. And because it can predict all of these at the same time, for instance, we can think from an algorithm fairness perspective, like on the adults data set, the task is to predict the income, but there's correlations with race and gender. And so when a generative model is trained to predict the data, just to only understand the structure of the data, it can automatically get good performance in all 3 of these categories at the same time. And so that's kind of can become a concern easily for fairness when we're then applying it to some downstream tasks. And when we apply it to classification, we're not really seeing how all the structure relates with one another. But when we do this structure learning or this generative learning, we can look at, for instance, the most important connections that we've learned and how kind of some income and gender are not directly connected, but they have a bunch of variables through which they can be proxied and have some correlations. All right, I'll try to just quickly wrap everything up. But yeah, so there's Gaussian decomposition and what we looked at today, which can be thought of as many-body tensor decomposition. But then we could be interested in latent variables, which can quickly expand the capacity. So Gaussians are simple models, but when we do a mixture of them by some latent, we can get a very significant increase in the modeling capacity. And there's recently been some connections with the same ideas for many-body tensors to the more typical tensor decompositions, such as low-rank decompositions. And that's actually some active and ongoing work here at Regen. But yeah, this is one important direction for being able to understand how well this many-body tensor can actually approximate the data. And then I just want to kind of end with some future directions kind of as we're thinking about this. So maybe I'll mention the last one first. So these higher order interactions that we can model, they're fundamental, but are they good enough? Or like, what about the interpretability? Because if we have to go to 4D, 5D, etc., it becomes harder and harder to visualize. So maybe we need these latents to be able to kind of reduce the simplicity back to something that we can visualize or understand. So even though there's some latent variable, which we don't have a statistical certainty on whether it exists or not, maybe that will still give us more simple models. There's also the other simple biases of decision trees or nearest neighbors. Maybe those are some other directions which have better inductive biases for certain problems. And then I'll just also mention the recent focus on generative tasks. So a lot of work in explainability and interpretability is focusing on prediction tasks. But for AI people, like realistic images and realistic text are now possible with diffusion models and LLMs. And there's no like obvious explainability and interpretability applications, although of course there's increasingly more and more applications, but this is definitely a future opportunity for the field. So thank you so much for listening to my talk. And then we can take any questions.
Okay, thank you very much for the very nice talk. If there are any questions, I think you showed us your architecture in the first part of your talk. I was wondering, because you have this additional additive structure in your total architecture, does it help to make each one of the networks like simpler or more shallow or something like that?
Yeah, so I guess you could be interested in this architecture because, because it's, sorry, it's kind of blocked here. Yeah, so because it's a simpler model, then like, does it need to have the same capacity as the original neural network? Definitely. So I didn't explore it too much. Like you could try to really push it, but they would definitely were much smaller than the original model. So I think it was something like, I'm not going to remember the exact numbers, but let's say 1,000 hidden nodes, 3 layers for the original network. But then these are only like 16 or something hidden nodes for each of the 3 layers. So there's a lot less information that needs to be handled by them, and they can become a lot simpler. Yeah.
I see. Interesting.
And then also, I didn't mention it, but we can apply this exact same procedure to the other popular method. So there was one other GAM method which outperformed us on one data set. But if we apply the procedure of interaction selection, then we can get an even greater boost in performance with that model type. And that model type is like a closer to a differentiable decision tree type structure instead of a neural network structure.
Oh, okay.
Yeah, and that's getting into the kind of functional biases where decision trees can easily map like these gaps or like discontinuities between the data. So decision trees are much better at that, whereas a neural network tends to have like a smooth sort of approximation of the data.
Okay, if there are no more questions, let's end the seminar. Thank you.